I'm recording. We're live. We're going here. No, we're not live. Yesterday I talked about the mole, right? And then we determined something called the molar mass. And we then used that molar mass to do conversions between mass and moles. I did that backwards. I should have prompted you. I should have said, how do we convert mass to moles? See, very good. My afternoon class does not enjoy this whatsoever. The afternoon class I had like 3 molar mass. Everybody else is like, that's dumb. So yeah. Would Jared do this? Jared is only in grade 10 science, so he haven't dealt with. You told him to say molar mass? Oh, no, he did not. No. All right. Okay. Let's continue. So now we've learned how to convert from mass to moles using the molar mass. We can convert from moles to entities using Avogadro's number. And if we want to break apart the compound entities into little individual entities, is that what we kind of concluded to call it? We can use this one that we have to sometimes generate if we need to do that. All right. I told you that there is going to be a quiz on Friday, and it's going to be on all that stuff that we did the last 2 lessons, essentially. Okay? The lesson we're doing today is not really that long of a lesson. I don't want to move on to a new one after this, so I'll do today's lesson, give you some homework, but then you'll probably have time to even work more on that mole stuff if you didn't quite get it all completed. So you might have time to take a look at that, or even maybe just study it and get prepared for the quiz tomorrow and ask me some questions. Okay, so for today's lesson, we're going to be kind of stepping away from the concept of the mole, and we're going to look back kind of historically at how chemists would have originally come up with the original concept of a formula. If you think about it, it's really kind of a tricky thing to start with no knowledge of atoms and then come to eventually a point where you can say that a water molecule is definitely made up of, H2O, 2 atoms of hydrogen and 1 atom of oxygen. Or we could even talk in moles. A mole of H2O would be made up of 2 moles of hydrogen atoms and 1 mole of oxygen atoms, right? Remember, we can now talk between either moles or just individual atoms. It doesn't matter. It means the same thing. So this is a little bit of a preview of how chemists came about to determining and going from just doing reactions like the alchemists, taking some coal, some carbon, and burning it and producing carbon dioxide, and just doing that as a reaction and not even thinking about it, to really knowing exactly what's happening on an atom-by-atom basis. In previous curriculum, where the units were in different orders, we actually talked about this stuff very, very early in the course, because in previous curriculum, the people who wrote it had the idea of, let's talk about atoms, and then let's get right into talking about how they figured out how those atoms were in certain proportions, like in H2O or CO2. And we need to do calculations like this in order to figure out those ratios and those proportions. They've shifted things around, and so now it's in this position in the course, but it's not a big deal. I'm going to show you how we determine a percentage composition in 2 ways. Well, first I'm going to explain what a percentage composition is. Then I'm going to show you how we calculate it in 2 ways. The first method that I'm going to use is starting with the formulas that we already know, all right? It's kind of like, calculating a percentage composition with us sitting here in 2013 with the knowledge of all of the chemists behind us. And so we can actually take a formula, take that knowledge of that formula, and eventually figure out a percent composition. It's like knowing the answer and working backwards to get the question. All right, that's what we're going to do with one method. So we're going to take our current knowledge of the formula and figure out a percent composition. Then I'm going to show you how chemists like Lavoisier, well, Lavoisier might not have done percent, oh no, he would have done percent composition, sure he would have. Guys like Lavoisier doing the first kind of labs with the scales would have taken the masses that he obtained from his scales and then also figured out a percent composition, all right? So we can actually calculate this from two different points of view. And you'll find as you go through science, you can always really calculate something from two different points of view. Starting with the formula is like starting with the theoretical side. In theory, we believe that water is made up of 2 parts hydrogen and 1 part oxygen. And so from that theory, we can figure out what the percent composition is. From the other side, it's from experiment. Someone actually does an experiment, they get some masses, and from those masses, and not even knowing what the formula is, do some calculations and figure out the percent composition. So we're going to look at it from both ways. Normally, I would follow up with a lab tomorrow where we're going to combust some magnesium and figure out the percent composition of magnesium oxide. But Mrs. Murray is doing the same lab with her grade 12 college class also tomorrow, so we're going to be bumped back to Monday. We'll do a lab. So I might make reference to a lab, and that lab's going to happen on Monday just because she's using the lab tomorrow. All right, so let's first talk about what percent composition is. Well, it's a very straightforward concept. It's the percentage by mass, so we're looking at the mass of each element in a compound. So really, when we say percent composition, it's a mass percent. How much of the mass of an entire water molecule is oxygen, and how much of the mass of an entire water molecule is hydrogen? So it's a very straightforward calculation. I was going to try to talk or expand on it, but I don't think we need to. Let's just go to an example here. Determining the percent composition using chemical formula. Determine the percent composition of, and we're going to start with water. Now I'm going to be looking at masses because it's a percentage by mass, so I'm going to need the formula of that. Now this is from theory. We believe that water is H2O. And I want to know what the percentage of the mass of oxygen is in that H2O and the percentage mass of hydrogen is in that H2O. Let's first talk a little bit about what percentage means, because there's not going to be a magic formula for this type of problem. We have to think it through. So when you get a test back, we're all great at percentages. You figure it out right away. As soon as I give you the test back, what do? If you've got, say, a certain knowledge mark, how do you figure out the percent? Yep. You take the mark, right, and you divide it by what it was out of. What do we really mean by what it was out of? What is that value? It's the total. It's the total that you possibly could have obtained. And that's always the case for all percentages. You take the thing you want to worry about, in this case, what you got. In other words, it's actually the number that you got correct, right? Divided by the possible total that you could have got correct, and then times by, did you say times by 100? Times by 100. So you take what you got correct, divide by the total, always the total on the bottom, times by 100. What you're calculating there is actually percentage correct, all right? Let's say you got 8 out of 10, 8 divided by 10 times 100, 80%, percentage correct. We could find out a different percentage. We could find the percentage incorrect. There'd be nothing wrong with that. We could do that calculation. You'd take the number you got wrong, in this case 2, divided by 10 times 100, and you'd have 20%. 20% incorrect. You should try that sometime. If your parents say, what percentage did you get on that test? Let's say you did really crappy. And you say, what percentage of did you get on that test? They're not specifying which percentage, whether it's correct or incorrect. So let's say you got like 40%. You really tanked it. You say, what did you get on that test? I didn't do too bad. I got 60. Wrong. Oh, all right. Well, did you know what you did wrong? Yeah. Oh, yeah. Yeah. Can you fix it? Oh, yeah. Yeah. All right. As long as you do better next time, you got it. You got it sold right there, right? That's a little loophole you could work on. Just keep that in mind. Same thing here. We're doing the exact same thing. Oh, by the way, percentage correct plus percentage incorrect, what should that equal? 100%, right? It should always total up to be 100. It's exactly the same with this. If I want to find a percentage by mass of water, what am I going to need on the bottom of my percentage, or the bottom of my fraction? Yep. Not 100% necessarily. It's going to be times 100, but what needs to be on the bottom of that fraction or that ratio that I'm calculating? The total mass. That's the first thing we need. Let's get the total mass. Maybe some of you already have. This one's an easy one. Again, I told you if you have this memorized, you don't need to write the steps, but this actually has some purpose. 18.0 grams per mole. So now we want to find the percentage by mass of all of these atoms. So percentage hydrogen. What am I going to put in there? What's my fraction going to look like? Yep. 2/18 times 100. They have both the same units, grams per mole, grams per mole. They'd cancel out. And what do we get there? Yep. 11.1. That's good because it should be 2.0, 18.0. That's only two significant digits, but 11.1% is good. Now, under normal circumstances, if I'm doing this on the board, I would put this underneath it, but I'm going to put it to the side. You can put it wherever you'd like. Percentage oxygen. How am I going to calculate that? Yep, Joy. 16 divided by 18 times 100, and what do we get? Yeah, Dallas. Sorry, I just couldn't hear you very well. Let's go to one decimal. 88.9? 88.9%. What has to be true about these two percentages? Yep. You have to add to 100, and if you do a check, please check it 100%. Normally I like to do this above and below each other because then I'll have the 11 above and the 89 or the 88 above it, and then I just add them down. Anyway, you get the idea. Some of you might say, couldn't we just figure out the percentage of oxygen by subtracting it from 100 because there's only 2 atoms in it? You're right, you could. But it's good to just check sometimes. And if we have more than 2 atoms, then you can check to make sure you did the other ones correctly by doing that third calculation. Let's do a couple more examples here. Chromium 2 phosphate. Now I'll see if I can do this one above and below each other, and I'll use my space a little better. So again, we're getting very good. If we see a name, we're going to need a formula, right? Because we're going to need to get some masses. So does somebody have a formula for that chromium 2 phosphate? Jory thinks she does. I can tell by the look on her face. CR3, PO4, 2. Excellent. So we've got a lot of atoms in this thing. And I don't normally use a phosphorus. 31.0. And chromium, definitely don't use chromium. You can tell me, but I can walk over here. What do we got? 52.0. You got the total? 294, 294.0, yep, grams per mole. We're not so worried about the grams per mole unit, but it's important to put it. So percent chromium, and I'll try to do these all above and below each other, percent phosphorus, percent oxygen. Those are the calculations that we want to do. Now here's a neat thing. You let your calculator run all the way through this thing. Oh, we don't have a correct number. 346? Did we not multiply something here? I got to fix the eraser. 346.0 grams per mole. All right, thank you very much. So you run through the calculations, and you don't even think about the 16 times 8, what that's actually equal to, or even the 52.0 times 3. And now we've got to figure out how much chromium there is. You don't need to actually know what that value is to write it down. To get the percent chromium, we can go back to the chromium line, and we can simply write 52.0 times 3 and put that over the 346.0. So notice what I've done. I've pulled out that little calculation for the chromium. I still don't know what the total of the 3 chromiums are, but you know what? My calculator is going to calculate it for me anyway, and if that saves me a moment or two while I'm doing a test, that's fabulous. Again, the calculator is going to take care of the Bedmans for me. 52.0 times 3 divided by 346 times 100, bang. What do you got? 45.1? 45.1%. And we will do the same for the rest. Now, the only little pitfall that I find some people fall in when doing it like this has everything to do with the way I set up the arrows. Chromium is the first one, but look at, in the mass total, it's the last value. I've seen some people moving in a hurry during a test take the 16 times 8, put it there for the chromium because they think first, and it's not. Make sure you pick the right numbers. So for the phosphorus, 31.0 times 2 divided by 340, oops, that's a 6.0 times 100. And then now our 16.0 times 8 over 346 times 100. And when you get a big, this is not a molecule, this is a formula unit, but when you get a big entity like this, here's where there's some value in calculating each of them on their own and checking to see if they add to 100. So I'll take some percentages as you get them. Yeah, what do you got there, Haley? 18.0%. And any more? Nope, we don't like it. We got some frowns there. We're getting frowns. 17.9, a rounding error. That's not bad, but we'll do 17.9. This slide's going to be a mess. Here, we'll just scribble it. There you go. Got to fix the eraser. I think there's chalk dust in my eraser port. And what about the last one? Yep, Maggie? 37.0. This is a 17, isn't it? I scribbled out my 1. 37.0%. And check. 100? Excellent. 100%. If you get like 99.9, you made a rounding error somewhere above, right? And I'm not really too picky on that. You know, I'm not like, I'm more concerned that you do the process right than if you happen to drop a rounding thing. I'm not that concerned, but it's good that we get it correct. So that's how you determine. Do I have one more? I don't even know why I would have one more. So that's how you determine percentage composition from the formulas. Now what that says is the homework, and it just says questions here, but that's the homework right there. It's that reference right there. Now I'm not going to let you work on this right now because I'm going to talk about how we would do it from experiment, and then give you a few more little questions, and then I'll let you work. So this is how we determine the percent composition from a theoretical standpoint. In theory, we believe there are atoms. We're getting to the point where we can almost see them. In theory, we believe these atoms have electrons and they trade them or they share them. In theory, we believe that if we do a crossover of their oxidation state, we can get the formula. And in theory, we believe they have masses as stated on the periodic table, and therefore, in theory, we believe they have this percent composition. In an ideal world, we should be able to do an experiment and get the same percentages. And if our experiment supports our theory, that makes our theory stronger. So let's talk now about how we would actually get a percent composition in an experimental standpoint, or in an experimental point of view. And this is exactly what our experiment on Monday is going to be. It's going to deal with determining the percentage composition of magnesium and oxygen and magnesium oxide. You know how to determine the formula of magnesium hydroxide. So in the hypothesis, you will determine theoretically what the percentages should be, just like we just did now. And hopefully, by the end of our experiment, our theory in our hypothesis is the same as what we calculate in our experiment. The nice thing about our experiments from this point on is that they're very numerical. We're now going to start with numerical data, which is nice. We're going to see if we can get the right data. So in this case, you'll notice it's kind of like a word problem. And there's just some masses in there. We're not worried about formulas. We're not converting anything into moles today. We're just using percentages. And it's the same thing here. We have 3.45 grams of sodium metal. It reacts with some chlorine gas to produce 8.78 grams of sodium chloride. Determine the percent composition. Well, what do we have in this question? We have a mass, oops, better write it down. We have a mass of Na that we started with. And that is 3.45 grams. We don't care how many atoms are in there. We don't care how many moles are in there. We could calculate it, but we're looking at it from a standpoint of experiment. We're not thinking about theoretical moles or things like that. I have a mass of NaCl, and that's 8.78 grams. And eventually, I want to know the percentage of the mass that is sodium and the percentage of the mass that is Cl. Well, we're not dealing with masses of atoms in this case. We're dealing with just masses of stuff. I have the mass of sodium and the mass of sodium chloride. What could I get from that? Yep. Sure I could. Mass of the chlorine, I can get that as well. Now that's not necessarily Cl2, it's actually chloride, but that's okay. And how would I get that? What am I going to do? Yeah, this is basic stuff, right? You have done this type of thing, who knows when, like maybe finding volumes or something. This is very simple stuff. We're just subtracting. 8.78 minus 3.45. And what is that number? I'm not going to try to do that in my head. Yep, Maggie? 5.33. 5.33 grams. So this is still a percentage. It's still going to be what we're interested in over the total. So what am I going to put in there to determine the percentage mass of the sodium? Dallas? What do you think? Still a percentage, just like a test. I need to put what I'm worried about, correct answers, over the total, what it's out of. Still the same thing. Dallas? 3.45 over 8.78. You bet. Even though we can't see the molecules or atoms or formula units or ions, from our experiment, we started with 3.45 grams of sodium, and that produced 8.78 grams of sodium chloride, which means even though we can't see the little pieces, we can still make a percentage of the mass of the total. 5.33 grams over 8.78. If I do it right, it should add up to 100 times 100. I'll take some numbers if you've got it. And it's 3 significant digits for sure on this one. Tyler's looking at his calculator. Are you looking at a number, or are you just kind of staring at the buttons? Do you have a number of this that might be correct? Oh. And then you cleared. Somebody else have it? Yep. 39.9? 39.9%. 39.3, so it's just my old guy hearing. It's the machine. It's noisy, isn't it? That's a noisy machine. Now what do we have? Lots of hands up. Are you telling me the next one? Or is there a mistake in this? It's good? Jory, what's the next one? I couldn't hear that. 50.7? 60.7. I could have determined that just by looking at it. 60.7%. Does it add up to 100? 100%. Again, it has to add up to 100, right? I took the 5.3 by getting the other half of that thing. I subtracted it off. But still, it's good to check it. And ideally, if this experiment was done well, then that should be the same as the percentage composition if we just looked at NaCl and got the total, all right? So that's how we would get it from experiment. That was a very simple example. Let me give you a couple more examples that have maybe some twists to them, but they're not complex. Again, all we have to do is figure out what's the mass of the stuff we're interested in, figure out what the total mass is, and just turn it into a percentage. And if you see how to do this, don't wait for me. We do have to assume that we're dealing with only hydrogen and oxygen, and we know that that's the case. What am I putting in my first percentage here? Somebody tell me what I'm putting in there. Is that a hand up, Dallas? No, that's just holding your pen in a particular fashion. Yeah, what do you got? 2.5 grams over 18. The experiment shows that 2.5 grams of hydrogen, when completely reacted with 20 grams of oxygen, produce water. Water is 18, but I don't know that. This is an experiment. I don't know theory. I don't know the theory, so I can't use 18. No. That you've mixed up the theoretical part with the experimental part. Janessa, what do you got? How did you get 22.5? You add them together, because in this case, I tell you that the 2.5 grams react with the 20 grams. So if we really wanted to write it out, mass of hydrogen, 2.5 grams, mass of oxygen, 20.0 grams. So the mass total, or, the water, I guess, in this case, 22.5 grams. You know what? No need for me to see that. It's pretty obvious. But if you do need to write that stuff out, that's a good thing if you want to write it out. So yeah, 22.5 grams times 100. 20.0 grams over 22.5 grams times 100. And I'll take some numbers. Yep, what do you got there, boy? 11.1, hey, this sounds familiar. And is it 88? 88.9%. Does that equal 100? And that's exactly like what we got from theory. Now, Okay, we made up these numbers to make it work. How would they have actually done that in the beginning? They probably wouldn't have actually reacted that way. In an actual experiment, what chemists would have done is they would have used that Huffman apparatus. Remember the Huffman apparatus? It would have looked like a big H, plugged it in, bubbles, 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 right? You've got the H and the, if we could then measure the masses of those gases, which you can. It's a tricky thing to do to weigh gases, but you can do it. We could have then weighed how much hydrogen and oxygen came from the decomposition, and we could have got the exact same numbers. That's the way they would have determined the percent composition the first time that they analyzed water, all right? Okay, and now one last example, I believe. Hold on, I'm checking ahead here. Yep, one last example. Now this example is more like the actual experiment that we will be doing. We will be taking some magnesium metal, a strip of magnesium. We're going to clean it off, make it nice and shiny so that there's nothing on the outside except just magnesium. We're going to put it in a crucible, and we're going to heat the heck out of it. We're going to cook it. And we're hoping that the oxygen in the air reacts with all of the magnesium in the crucible. And then we're going to get information like this. So we're going to have a nice data table. We're going to have information like the mass of the crucible and lid empty, because we're going to have to do some subtraction just to get some numbers. So we'll weigh the crucible and lid first, nothing in it. Then we'll put our nice clean magnesium in it. In this case, we've got copper. In our case, it's going to be mass of crucible, lid, and magnesium. Then we're going to heat the heck out of it. We're going to let the oxygen in the air react with it. In this case, they must have had some sulfur also in the crucible, I would think. Don't worry about that in this case. So in this case, at the end, after it's reacted with the sulfur, we've got the mass of the crucible lid and the copper 2 sulfide. And we have lots of significant digits because we've used a very accurate scale. Our scale isn't that accurate. Our scale is only 2 decimals accurate. But significant digits are going to be very important on our experiments. Significant digits come from measurement. So we're going to be doing actual measurement. We have to round to proper significant digits. And at this point, we need to figure out things like mass of the copper and mass of the copper 2 sulfide. Sorry, is it sulfide? I don't need an O. CUS. And ultimately the mass of the sulfur. So the trick to a question like this is to take our experimental data, do some thinking and some calculating and figuring out those masses. Once we have those masses, you do the exact same calculations. How am I going to get the mass of the copper? Tell me the numbers I have to do with what? What do we got there, Dallas? Both grams, excellent. Crucible lid and copper minus the crucible and lid. And do you have an answer for that? Sorry, 1.4. You'll notice I actually can't round that to 4 significant digits because there's no digits left. When you subtract, you don't round to significant digits. You actually keep the same number of decimals. So it means that these 20s canceled away, and now I'm left with only 1.014 grams. We don't like that number? 1.013. That's significant. Grams. I wrote down the wrong number, or? Okay. How am I going to get the mass of the copper 2 sulfide? Well, just tell me the numbers I got to put in there so I can get it. Brody, what do you got? 776 minus 511. So again, total mass, subtract away the crucible, and what do we got? And all of these numbers are very important. All of the digits are significant. We actually measured them. We don't want to throw them away. Eventually, I'm going to need just the mass of the sulfur. Yep, Brody. What two numbers there? Tell me the numbers you're dealing with here. Just tell me some numbers to put in here. That'll work. You could have even subtracted the crucible lid and copper 2 sulfide from crucible lid and copper. It would get you the same answer. We've just taken away this down here. What do we have as a value? Yeah, Chelsea, what do you got? 252 grams. Okay. Now we get our percentages as per normal. And I don't have enough room. I'm going to just go on to the next slide. I'm going to need some assistance because I'm never going to remember all those digits. You have them written down, I assume. We have all those digits down. So I'm just going to go on to this other slide here, and I'll do the answers. So percentage copper, percentage sulfur. And I'll take some numbers from whoever has numbers to put in so I can get the answer once you've got it written in. We're going to encounter percentage calculations, I think, 2 other times, maybe 3 other times in chemistry. It's not necessarily going to be percentage composition. But keep in mind, a percentage is easy. What you want to find over the total, always. Abby, what do you got? Just tell me all the numbers you got there, and then the total. Yeah, I do. I want the total mass of the copper, or sorry, the mass of the copper over the total, because I don't know what those numbers are. Is that the right number to write? Yeah, let's keep going. 3? Yep. Times 100, and what do you got? 80.08%. Excellent. That's to 4 significant digits. Excellent. That's good, because 100 is like a perfect number. It's got lots of significant digits. And keep going, Abby. What's the next one, or do you have it? Yep. 252. 265 times 100. 19.92. 92%, and that has to be, and that does add up to 100%. So that's how we would deal with a question that would come from a true experiment. And we are going to do that type of thing on Monday. Okay? All right? And that is the end of my little introduction to percent composition. I don't really have enough time to start in on a new idea. I don't want to because it would conflict with it. But tomorrow we will start with a new idea. And then, like I said, Monday is going to be our experiment. Yep. No, just that page. Yeah.